Chapter 1, Exploring Data, and let's look at Section 3, Describing Quantitative Data with Numbers. So we got quantitative data, and from this we want to use some numerical descriptions such as calculating measures of center, the mean, the median, calculate it and interpret measures of spread, such as the range, the interquartile range, standard deviation, choose an appropriate measure of center and spread in a certain setting, identify outliers using the 1.5 times IQR rule, make and interpret box plots of quantitative data, and use appropriate graphs and numerical summaries to compare distributions of quantitative variables. The most common measure of center is the ordinary arithmetic average, or the mean. It's what we use typically when we say my grade average. To find the mean, X bar, of a set of observations, add their values and divide by the number of observations. Of course, most of you guys have done this for years, but this is really to show you the notation. So as we get further into the course, this is comfortable and familiar to you. So if we have a bunch of observations, the first X, the second X, the third X, all the way to the nth X, so that's X sub 1, X sub 2, all the way around the room till we get to the last one, their mean is going to be found by taking the sum of those observations and dividing by n, the number of observations. In mathematics, we use a capital letter sigma, a Greek sigma, to mean add them up. Therefore, the formula for the mean can be written in this compact notation. Again, I don't really expect you to use this formula to find the mean because I think you're familiar with it, but this is how we would write it. Add up each individual X and then divide by the number of observations here. That gives me X bar. If I had two lists of variables, maybe an X and a Y, then I have an X bar and a Y bar. Another common measure of center is the median. The median is the middle or the midpoint of the distribution. It's the number so that half the observations are smaller and the other half are larger. Now, we probably have known this for a while. You've used median before, but there's a couple little tricks that we want to make sure we keep in mind. First of all, to find the median, first we need to arrange the observations from small to big. Put them in order. If you don't do that, the middle number doesn't make any sense. If we have an odd number of data points, then the median is just that middle number. So if you thought of the 5 data points being like your fingers, your middle finger would be the median. On the other hand, if we have an even number of data points, the median is the average or the mean of the two center observations. So if you held your two hands out, we now have 10 fingers. The median is halfway between the 5th and 6th point. So in this case, your thumbs, and the average or the mean of those two data points would be the median. So here's a list of 20 data points. We asked 20 New Yorkers, hey New Yorker, how long does it take you to get to work? The individuals were the New York workers, and they gave me a quantitative response. There they are. If I'm going to find the mean, I simply add up all those numbers and divide by my 20 New Yorkers to get 31.25. If I want to find the median, I could look, for example, here's a stem plot, and I could look through this list of numbers. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the 10th and 11th data points are these ones that are bolded. So my mean, the mean of these 2 points, the mean of 20 and 25, is the median. So the median for this set of data is 22 and a half, the middle of those 2 points. Notice that neither the mean nor the median has to be an actual point in the data. Both of these are measures of center. They both tell me where the center of this data is. They just use different mechanisms for finding the center. Sometimes the center can be misleading. So we want to include something about the spread. How spread out is the data? One way to do that is with what we call the quartiles or the interquartile range. For example, when I talk about the spread being misleading, how many workers here traveled 31 minutes? Well, none of them. How bad is the commute in New York? Well, for this guy, it wasn't very bad at all. For this guy, it was nearly an hour and a half. So looking at the spread can tell me how spread out my values are. The interquartile range is related to the median. To find the quartiles, the second quartile is actually the median. To find the first quartile, it's the median of the left half of the data, and the third quartile will be the median of the right half of the data. The interquartile range is just the distance between Q3 and Q1. So let's look at these numbers. Here were my numbers of the New Yorkers. We transformed them and put them in order from small to big. Now we said a second ago that this was the middle, and so the median was 22.5, right in between here. Now if you notice over here on the left side, I've only got 10 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The median was right here, so the left has 10 data points. The average of these two numbers will be Q1, and likewise the average of these two numbers will be Q3. The interquartile range then is the distance from Q1 to Q3. Subtract those two, and that tells me a measure of spread. Now, frankly, right now, you probably haven't done this a lot, and so your ability to really understand what that's telling you is a little bit limited, but as we get more familiar with concepts like IQR and other measures, they'll make more sense to you. This tells me that the middle 50% of workers, the ones that are in here, have a spread of about 27 and a half minutes, or have a range of 27 and a half minutes. They're spread from 15 to 42 and a half. Range, or IQR, is one number, so we actually subtract them and get that one value. The range is just one number, or the interquartile range is just one number. From the IQR, we can use a concept listed here to find outliers. Previously, I defined an outlier as a point that simply lies outside of the pattern. Well, we want to put a finer point on that and say, what does that mean outside the pattern? So we have a rule, 1.5 times IQR, and the story is that Professor Tukey, who actually invented the box plot, invented a lot of stuff that we use in statistics now. He passed not too long ago. He was talking about this rule to his students, and they said, why is the rule 1.5 times IQR? And he said, well, I thought that 1 was too small and 2 was too big. And so the idea is, one, that Professor Tukey just came up with it because it felt right. Now, it felt right because he had a lot of experience dealing with data, but it wasn't scientifically derived. And the other idea is that, I don't know what the other idea is. I just forgot. I don't know. Maybe it'll come back to me in a minute. So there's Professor Tukey's rule on 1.5 times IQR. So let's see what that means. What it means is this. For our New York travel data, we found the IQR was 27 and a half. If we take that number and multiply it by 1.5, we get this. Now take this 41.25 and go to the left of this number and to the right of that number. So go outside of my quartiles, another 41.25. So Q1 minus that 41.25 and Q3 plus that 41.25. These are sort of bounds on what Tukey thought might be typical data. So if we had points that were outside of that range, he thought that would feel like it was too far out and would therefore be an outlier and worth considering. Perhaps there's some reason why that number looks pretty different than the rest of the data. So in this case, think travel times less than this or more than this would be considered outliers. Obviously, we don't have anything like that, but we could have numbers that are bigger than 83.75. In fact, we did. If you recall, we had one traveler who commuted 85 minutes to work. We would consider him an outlier. Very different than the rest of the data. The 5-number summary then comes from the quartiles, and if there are, of course, 5 numbers in the 5-number summary, they are listed right here. The minimum, Q1, the median, Q3, and the max. Minimum, Q1, median, Q3, max. Those are the 5 numbers in the 5-number summary, and they will give you a pretty good idea of what a data set looks like, especially if there's a bunch of numbers in the data set. That 5-number summary leads straight into a box plot. Here's how to make a box plot. Make a box from Q1 to Q3, put the median in there, put whiskers out to the smallest and largest observations that are not outliers, and then we, in a modified box plot, will mark outliers with an asterisk. So here was the data again from the New York travelers. The median was 22.5. The quartiles were 15 and 42.5. So that makes this box. This side of the box is more spread out because 22 and 42, or 22.5 and 42.5, are more spread out than 15 and 22.5. Those numbers are closer together. The minimum will go down here where that 5 is. Now the maximum is an outlier, so 65 is the biggest non-outlier, and we'll put a dot out here where 85 is. Now sometimes you'll see regular box plots where they'll just extend this all the way out here, but sometimes we like to differentiate on the graph what an outlier is. Notice this is the biggest point in the data set that's not an outlier. This is the smallest point in the data set. The fence, or that guideline, is actually somewhere out here, and we typically don't mark that on the box plot itself. I think it was 83 point something, and we had a negative number for the fence down here. Those don't show up. So there's my modified box plot for travel time of New Yorkers. Now, if I think about the median, I use interquartile range to discuss the spread. If I think about the mean, I'll use a measure of spread called the standard deviation. So consider the following data on the number of pets owned by a group of 9 children. I said, hey child, those are the individuals, how many pets do you have? And they responded with a quantitative value, and I made a dot plot of it. So one kiddo has 1 pet, one kiddo has 3 pets, 3 kids have 4 pets, and one lucky kid has 9 pets. There are 9 children, so there should be 1, 2, 3, 4, 5, 6, 7, 8, 9 dots. First thing we want to do to find the standard deviation is to find the mean. After we find the mean, we're going to see how different each number is from the mean. So we could add these numbers up and divide by 9, and we would discover that the mean, the x bar, is 5. Now we want to look for each of these numbers and see how different they are from the mean. So this guy was 1 minus 5. This one is 3 minus 5. This is 4 minus 5, 4 minus 5, 5 minus 5, 5 minus 5. So I'm finding all the deviations between the mean and each of the data points. There's my list. Here's the numbers. Subtract the mean from each of them. Here's what I get. And so I want to find the typical deviation, the standard deviation. So I'm going to add these numbers up. -4, -5, -6, -7, -8, -9, 8, 7, 6, 5, 4. Those add up to 0. And as you'll discover, they always add up to 0. Therefore, since they always add up to 0, I'm going to square them all first. Square each deviation to get these numbers. add these squares up, that'll be the sum of the squares of the deviation. Divide by something called n minus 1. This is called the degrees of freedom. So in this case, I had 9 kids. I'll divide this sum by 8. That value, the sum of the squares of the deviations divided by 8, is called the variance. Take the square root of the variance, and I'm back to the standard deviation. So in this case, these numbers all added up to 52. I divide by 8 to get 6.5. That's the variance. The square root of the variance, 2.55. That's the standard deviation. I encourage you, if you're watching this, to pause the video and run these numbers through your calculator to make sure you can do this on your own. The standard deviation measures the average distance from the observations to the mean. It's calculated by finding the average of the squared differences and then taking the square root. The average square distance is called the variance. Standard deviation symbol is S of x. This is the standard deviation of the x's. For variance, it's S of x squared, because the variance is just the standard deviation squared. If I had another variable, like I had an x list and a y list, then this subscript down here would just be y. Sometimes, if there's only one variable, we don't put a subscript on there because it's obvious what we're talking about. This is a lowercase s. Standard deviation is the square root of the variance. Notice how we did it again. We summed up each number minus the mean squared. The sum of the squares of the deviations from the mean. In this n minus 1 business, that's called the degrees of freedom. So now we have a choice. We can use the mean and the standard deviation, or we could use the median and the interquartile range. So how do you decide? Well, if I have a distribution that's skewed, that really has something pulled out one direction, then the median and the IQR are typically better measures. On the other hand, if I have a roughly symmetric distribution, I don't have outliers, the mean and the standard deviation work better. And the reason is this. If I have a skewed distribution, so consider a right skewed distribution that's maybe income for a room full of 20 people, and in that room is, say, Bill Gates. So he's way over there to the right. The distribution is really skewed. If I use the mean to discuss that distribution, then it might look like the average income for the people in that room is millions of dollars a year. And the mean income is millions of dollars a year, even though most of the people in the room maybe don't make near that much, and one guy makes way more than that much. So the mean and the standard deviation can be heavily influenced by outliers. That's called non-resistance. They don't resist changing. The median and the IQR are a bit more resistant to those unusual values. And so when we have unusual values or skewed distributions, we like to use the median and the IQR to describe them. Note, numerical summaries aren't a complete description. Graph your data. Always graph your data, especially if you've already put it in your calculator. It's so easy to make your calculator graph it. Always want to have a look and see what you can learn from the graph. So as we get a little further into it, we're going to have longer questions, and this will be a theme that goes throughout the book. This four-step process: state, plan, do, and conclude. So first, state. What is it we're trying to figure out? That's what stating is. State what you're trying to do. Plan how you're going to go about it. What statistical methods should we use? What formula might we want to use? Do, okay, now actually graph it and carry out your calculations and show the work. And conclude, finally tell me what that tells us at the end of it. This will be a plan that we use throughout the course: state, plan, do, and conclude. So in this section, we learn to calculate measures of center, like the mean and the median, Calculate and interpret measures of spread like the range, the interquartile range, or standard deviation, which we also talked about variance. Understand which is an appropriate measure of center and spread given the certain setting, given the skewness or symmetry of the data, as well as outliers or their lack of outliers. Identify outliers using the 1.5 times IQR rule, and then make and interpret box plots of quantitative data. The process of doing some of this may look straightforward and simple as I go through it. I encourage you to practice a few problems on your own so that you can see where the stumbling blocks may be. That's section 3 of chapter 1.